So let's go ahead and start some of this. So what are we being asked to solve for? Okay. We're being asked to solve for grams. Okay. Really? Just grams.
Yeah.
Grams of sulfur dioxide. Okay. What were we given to start with?
Molar mass.
We were given 64.07 grams per mole. What else were we given?
That's the molar mass of a single molecule.
What was that?
Single molecule.
You were also given that you had a single molecule. So you're actually given two pieces of information to start this question. Okay? And we want to differentiate those pieces of information because we could change that single molecule to be 2 molecules, 3 molecules, 64,321 molecules. Can we change the 64.07 grams per mole? Why not? That is specific not to grams to mole, that is specific for sulfur dioxide. Okay, so that number can't change, but the single molecule could theoretically change. So we want to needle apart those two things and keep them as independent pieces of information. Okay? So with those two pieces of information, which should we start our solve with? Okay? So we've got a suggestion to start with the 64.07. In my walking around, nearly everybody started with that. I would argue nearly everybody started with that because it's a number. They didn't see that that was actually 1 molecule of sulfur dioxide. Because if we had rewritten that as 1 molecule of sulfur dioxide, you might have started with that. Right?
Fair enough.
Okay. So we want to be careful in selecting what we're starting with. Not just because it's a number, so I'm going to start with it. Okay? We have to know why we're starting with it. So then the next thing that I observed was cool. People were like, I'm going to start with 64.07. And the question that I would ask, right, where did you just place that number? Okay, so I'm hearing by the grams. There's no grams written there, so you can't tell me by the grams. Okay, so we could say we start at the far left, and that's fine too. We can make that adjustment. It's ultimately not going to matter. Where did we place that 64.07? We placed it in an implied numerator. Why did you place it in the numerator?
Because of its units, it's grams over.
Okay, so that's a hugely important observation that William just made. Because of its units. And I'm going to say no. Do you see any units written here?
Not yet.
No. Okay? And because the units aren't written there, you are guessing at the placement of that number. Or you're doing that placement based off of something you're holding in your head. Do you really want to let someone into your head? No. Okay, so if you don't want to let someone into your head to see what you're thinking about, don't be doing calculations in your head. Don't place the 64.07 in the numerator. What should you start with? Okay. I heard a grams per mole. Okay, and I would argue still, no. Okay, and here's why. Because in walking around, I saw this. Where did you place the grams? Where did you place the moles? So if I wrote 64.07, where did I place the moles? I don't know where I placed it. Okay? Okay? The placement of that now becomes questionable. And if you go through and write it like that, what you're saying is that we should use typewriters to solve calculations. Since none of you are using a typewriter to do this, that is a false statement. So what you need to do is interpret the question away from the typewriter artifact. What does that slash mean? That is a division. A division between what two things? Grams and moles is too specific.
Mass, numerator.
It's a slash showing a division between the numerator and the denominator. So anytime you see that slash, that's what it's differentiating. The very first thing in that list is what?
Mass.
Numerator. The next one is denominator. All we're really trying to do is really nuance the language of what is written there. Right? And for those people that don't think language is an important thing, go to another country that doesn't speak English and try to exist. Okay? Language is exceedingly important. You need to nuance the differences between it, because if you don't know that language, struggling is a mild way to put it. Okay? That could be difference between where's the bathroom and let me drink your urine.
What?
Like, that's a pretty big issue, right?
Oh yeah, major.
Okay? Because the person looking at you is going to be like, no, hopefully, no, and walk away from you.
About to get peed on.
Okay? Or you're about to get peed on. Okay?
Yeah, don't be talking about killing.
That's a big issue. Okay? The same thing's going to happen here, except the problem isn't that you're going to get peed on. The problem is you're going to get the question wrong, you're going to miss the question, and you could potentially fail the class. That's a big issue as far as I'm concerned. Okay? So what we're trying to do is differentiate those things. So when we go through and see this, 64.07 grams per mole, your focus is not 64.07, it's grams over moles. Where should I place the grams?
The numerator.
Why do I want to place it in the numerator?
Because the unit tells you to.
Because that's what the paper says. Grams over moles.
Because the way you wrote it as is the root numerator matches the grams, and then denominator.
I want to place grams in my calculation to the left in the numerator because grams shows up in the numerator and what I'm trying to get to. That's why I place the grams there. Okay? The slash is just a way to differentiate those things in that statement. But I can change where those things are located because it would be a question of multiplying or dividing. That's a big differentiation. Make sense? Okay, so what do I want to place in the denominator now? Moles. What number goes with the grams? Why do I know the 64.07 should be placed with grams and not with moles? In our given information, the number is closest to the gram unit. Okay? 1 would go next to the moles. Everybody see it? Okay, I wrote that too big, so I'm going to erase it while you tell me the next step.
Times.
Okay, and I actually made a mistake, so we got a times. I'm going to argue doing something out here, not the next step. We screwed up.
Grams of what?
Grams of what? Sulfur dioxide. Moles of what?
Sulfur dioxide.
Sulfur dioxide. All right? In this question, is the substance changing?
No.
No. So we could sometimes fall into the trap of just ignoring the substance. When the substance doesn't change, you're right. You don't have to pay attention to it. What happens when the substance changes? Now you have to pay attention to it. If you aren't in the habit of already showing that the substance is there and what it is, you may miss that important step. Make sense? Okay. So, do we have our answer?
No.
No. What's wrong with our work?
Get rid of moles.
Moles needs to disappear. I would place moles in the numerator because I want it to cancel out. Okay, and in particular, I would want moles of sulfur dioxide, the SO2. Okay, so I could go back to the question and say, am I given moles of sulfur dioxide?
No.
No, you're not.
You're giving a molecule, not mole, guys.
And I know that the spelling is there, like MOL, right? No. Unfortunately not. Okay. What's given in our question is molecules of sulfur dioxide. What we need is moles of sulfur dioxide. Okay? So since I'm not given moles of sulfur dioxide in the question, what am I going to need to do? I need to do a conversion. Okay? That's the first statement. The next statement would be, well, where can I find a conversion that relates moles of sulfur dioxide to something else? There was a suggestion for the periodic table. And you're right, the periodic table does provide a conversion factor for moles. Moles to what? It does not go moles to AMUs. Goes moles to grams. It's called the molar mass. So that conversion factor absolutely exists. What is that conversion factor? Shh. Anybody that didn't raise their hand can answer. What is the conversion factor that relates grams and moles? No. What is the conversion factor that relates grams and moles? And for those of you struggling a little bit, let's just take a second here. We're looking for the conversion that relates grams and moles. G and MOL. Right? On opposite sides of a line. Reread the question. The periodic table tells you the molar mass. Awesome. That is absolutely a valid conversion factor.
So we already have that.
So where would the 64.07 go? And what happens with this conversion factor? Everything cancels. You mean all the work that you did to establish where to place grams so that everything lined up and worked has all been undone? Yes. What does that mean about the conversion between moles and grams? That was a crap conversion to use. You got to find something else. What do I want to relate moles of sulfur dioxide to? Why molecules?
Because that's the only other thing you have.
I'll elaborate.
So look, you have one molecule of sulfur dioxide, and then you have 64.07.
So by looking at the rest of the given information, we know we have information about molecules. Okay? So if I can somehow convert moles into molecules, I can now bring in that missing piece of information, okay, that I haven't used yet. So that is one way to do it. And I would argue that's an awesome way to do it. That's a very good way to do that. Okay? The other option is there's only so many different conversions between moles and other things. Okay? When it comes to that conversions, we get moles to mass, periodic table already used. We also get moles to molecules, which is the one we're finding here, and then moles of one substance into the moles of another substance. Are we changing the substance?
Yes.
Oh, we don't want to.
No. So we already used one of them. The last one we don't want to use because the substance doesn't change, which means you have to use this one. Okay? So now the question is, what numbers should show up there? Where do I find that? What relates molecules and moles? Avogadro's, and I'm pretty sure I'm starting to spell it like avocado now. Is it A? I don't know. I think I'm right. Avogadro's number. Avogadro's number does what? It converts moles to atoms. Okay? Just like a dozen converts eggs into a dozen eggs. Right? But a dozen doesn't have anything to do with donuts.
So things to things.
Okay? Avogadro's number converts things to moles of things, a large number of things. What is the thing? The molecule is our thing. The substance is our sulfur dioxide. Okay? So what we could also do is insert here moles of things of sulfur dioxide. That makes that unit really long, right? So typically what do? We typically ignore the things after moles. And we just imply that missing piece, that missing thing. Okay? A thing must be a physical thing to grab a hold of. Okay? So one of the confusing, I'm going to say thing again. One of the confusing things, okay, that can come out of this is that you'll sometimes see people relate grams into this. And say 6.022 times 10 to the 23rd grams is 1 mole. A gram is not a thing. What is a gram? It's a measurement. Okay? It's not an object that you can grab. I can't grab a gram. I can grab a gram of something, but I can't grab a gram itself. Okay? So when we're talking about this conversion, it must be in relationship to things. Molecules are a thing, a physical object. So, what numbers go in? 1 mole is? Okay. What happens with our units? Moles cancel. And then I'd have grams per molecule of sulfur dioxide. What was I asked to solve for? Just the grams of sulfur dioxide. Well, how many sulfur dioxides?
1 molecule.
1 molecule. I meant to pick purple. What goes in the denominator?
6.022
Look up at what I wrote. What goes in that denominator? 1. If it's a number other than 1, what would happen to the number of molecules? It changes. Right? It was given as 1 molecule. So the number that goes in the denominator there can't be anything other than 1. What about a unit? That would change the unit as well. And what we were given was very specifically 1 molecule of sulfur dioxide. If I put any other unit there, it's not a molecule anymore. It's now a conversion factor. Does that make sense? Okay. Now when we go through and deal with our calculation, molecules cancel, and we'd be left with grams of sulfur dioxide. Okay? One of the biggest complaints that people will give me is that I don't tell you answers. Not really true at all, but, we'll work with it. Okay? Let's actually solve out what this was, what our answer is. So how would I go through and do it? Well, I would take 64.07 divided by 6.022, and I would enter that in the calculator. I would then also multiply by 10 to the minus 23. Is that what the calculation said to do? It said to divide by 10 to the positive 23. Why am I multiplying by 10 to the negative 23? The rules of exponents that we talked about. We can change where it's located, numerator or denominator, by just changing the sign on it. Okay? That makes my power of 10 in the numerator, which means I don't have to worry about weird power of 10 divisions through this process. Okay? So I'll enter that into the calculator. I'll get somewhere on the order of
1.064 times 10 to the negative 22.
Fine. I won't play with the math in my head. 22 grams of sulfur dioxide. Right? If you enter this into your calculator, one of the most common answers will be 1.0, or let's see if I can pull this off. 1.064 times 10 to the 24th. Okay? 10 to the 24th, not 10 to the negative 22nd. Okay, what happened was a calculator mistake when you entered your division. Parentheses are important. You can either include the parentheses or you can choose to not include them and very carefully track your calculations. If you're being asked for the mass of a molecule, what should the number be? It should be very, very small, because molecules are very, very small. Okay, so I should be getting this negative 22. Kind of, sort of? Okay. You should be running this through your calculator. If you're getting that positive 24, which I think I'm right, could be wrong on that calculation, but I think I'm right. Talk to me after class. You need to figure out how to use your calculator is what it's coming down to. It is 24? Yeah. Okay. So talk to me. We need to address that because I can't address that during the exam. Okay? Do it again. How many fluorine atoms are present in 2.25 grams of fluorine gas? Okay. I can understand why you would want to write something out like this. Okay? Because you are comfortable in the English language.
That's right, you are.
Okay? So fantastic. Hats off. Unfortunately, that comfort in the English language is going to massively slow you down.
Sorry.
You end up writing a whole bunch of text when you didn't have to. And for reference, remember how we started off where we said that conversion of how do you convert 2,438,000 inches into miles? Solve using only alphabetic text. And it was that page worth of text. And you're all like, this is awful, this is stupid, I don't want to do all this. You didn't want to do it when Greg asked you to do it. Don't do it when I'm asking you to not do it. Okay? Does that make sense?
Yeah.
Okay? So use the abbreviations we've been talking about through the semester. That was the point of the first 2 units. Okay? So I appreciate that you want to write out the English language. Okay? The English language is going to hurt you here. We're in chemistry now. You need to start getting used to the chemistry language. So how could I shorten this atoms of fluorine? Okay? I could change that to atoms of F. Okay? Why do we use the freaking preposition? Of?
Yes.
Why do we need a preposition? We don't. So delete that too. Okay? Remember, we're talking about scientists that went from 100 to now saying 10 to the second. Technically, we're writing more by doing that, but we're writing less because it's a small 2, not a big 0. Okay? That's how subtle of a difference we are and how lazy we are behind this. So show abbreviations in your process. Can we shorten atoms? We could potentially, we could drop that down to ATM. Okay? Effectively what we're doing is just deleting vowels. Problem with ATM as an abbreviation? We'll encounter that when you read chapter 13. Chapter 13, you'll, I believe, encounter that. That's actually the abbreviation for a pressure unit. So that's already used for a different system. So using ATM becomes a problematic unit. How often are you going to work with atoms?
And always, every day.
So when you go into lab, you've measured out atoms.
Yes. A bunch of them. Many of them.
Okay. You've measured out a whole bunch. You don't measure out atoms. So the usage of atoms is so infrequent that it probably doesn't warrant an abbreviation. So write it out as atom. Okay? An atom of F sounds weird, so I got to say atoms. Okay? So now let's push the other side. 2.25 grams of fluorine gas. Okay? What abbreviations could we make?
G.
We get grams is G. What is fluorine gas? F2. Why is it F2 and not F? When we talk about diatomic elements, they by default are diatomic as F2. When are they written as just the single element? When it's explicitly stated. You mean when it explicitly says atoms of F? Yes. That's when you can write F. Every other time, F2. For those of you who've got some distance into this solve, that might have been an issue you missed. Okay? Why are we placing the grams of F2 in the numerator? I mean, over 1, all I did was put the denominator in. Why are we placing it in the numerator? It's what we started with, so we just put whatever we start with in the numerator. Go back to exam 2, that distance calculation with speed. If you take the 2 pieces of given information and you put the very first piece of given information in the numerator, guess what happens? You're wrong. Placing the information in the numerator just because it was a piece of information to place is a bad idea. Okay? So we could make the argument that we aren't sure, and because we aren't sure, we're just going to stick it in the numerator and hope for the best. Why would we go in the numerator instead of the denominator? Because division sucks. Right? It's a lot easier to deal with multiplication. Right? Okay, so we could just make the assumption it runs there. Other things that we could do, grams F2. Okay? Grams is a measure of atoms. Well, that didn't work because the measurement changed. F2, F, that changed too. So deciding where to place that can be a tricky question to answer. So we take a stab at it and we hope for the best. Okay? If we compare across, both the measurement changed and the substance changed. So we got to convert. What do you want to do? Okay, so we're here, let's change the substance. So let's get rid of F2 and bring in F. Where do we find a substance conversion? Okay, point to a square on the periodic table that shows me the relationship between 2 different substances. Right, when we look at the periodic table, it tells me information about a single substance. It does not tell me the relationship between multiple substances. The periodic table is not the periodic table of substances. It's the periodic table of elements. So as a substance conversion, I can't use the periodic table. Where can I convert one substance to another? How many hydrogens are in water? What did you just come up with? A substance conversion. You converted hydrogen into water. You said you needed 2 hydrogens to make 1 water. That's a substance conversion. Where did you pull that information from? The chemical formula for water. Where's our substance conversion that relates F and F2? The chemical formula. Okay, and for those of you being like, you mean the thing right there? Yes. Literally the thing right there that tells me that there are 2 F in 1 F2. F. Okay. But now we have a challenge, though. What is our unit there? Unit is, 1 is not a unit, 1's a number.
Oh, the subscript is 1.
The subscript is 1, I'll accept that. What is our unit?
Fluorine.
Is fluorine a unit? Fluorine is a substance. A unit has what components? A measurement and a substance. What is the measurement in that? 2 what's of F? Atoms. What, 1 what of F2? Molecules. Molecule involves a whole lot of letters that I don't like writing. So I write MLC. Okay? If we now go through and look at that, we've done or attempted to do a substance conversion. Did that substance conversion do anything to this? No. Okay? So it's good. We've at least started our conversion process. We don't have our final answer. Can we cancel the F2s? We can only cancel units, not parts of units. This is grams of F2 and molecules of F2. Do those cancel? No. Right? So now what? We got to do another conversion. What other conversion you want to do? Right? I heard of molecules to grams. You can see how great I am at doing a straight line. Okay? Is our conversion, or does a conversion exist between grams and molecules? The 1.66 number is grams to AMUs, not grams to molecules. Okay? What's that? Don't do this one. There's a reason why we don't do this one. It doesn't exist. Okay? And that's where things become problematic. You're trying to attempt a path. You have to change and see if it works. That's not one that exists. Right? And I'm going to run out of space, so I'm going to have to erase that. So what do we want to do? I heard a gram to AMU. That's a possibility. Okay? The problem with the gram to AMU one is that you now have to memorize that number. Wasn't there another number you had to memorize? 6.022 times 10 to the 23rd, right? Grams to moles. Okay? So if you remember 6.022 times 10 to the 23rd, molecules equals 1 mole of molecules. You also have to watch out for the AMU one, which is 1.66 times 10 to the negative 24th, grams equaling 1 AMU. How many of you got all those numbers straight? Ouch. That's a bad idea then. Okay. So you are required to know Avogadro's number. What does Avogadro's number relate? Moles to things. What is our thing that we're looking at right now? We could say atoms of F. We could also say, at this point, we were trying to get rid of molecules of F2. So we could convert this into okay. That comes from Avogadro's number, which was molecules is 1 mole. The molecules would cancel. We've simplified. Did we simplify enough? No. So what do we need to do? We need to get rid of the moles. Okay, I don't have moles, so I'm going to have to convert that moles into something else. What do I want to convert that moles into? Okay, we could try grams. You'll find that's not going to work so well. There was another suggestion, atoms. We could convert it to atoms. All we're going to end up doing is undoing the stuff we've already done. What do we want to convert moles to? Why grams? I got this floating grams of F2, right? Did I want that? No, so wouldn't that be cool? If I could put grams of F2 in there, wouldn't it cancel? Yeah. What answer would I have if that happened? I would have atoms of F. I know I erased it. What was I solving for? Atoms of F. So if that conversion factor exists, that would be a fantastic thing that could solve all of our problems and we would be done.
And it exists.
Where does it exist? This is found on the periodic table. This is the relationship between grams and moles. The mass to mole. Molar mass. 38. So where are you looking to find that 38?
Fluorine.
You look to fluorine and everybody sees the 38 quite clearly next to fluorine on the periodic table.
No, but it's 19 times 2.
This is F2 as a molecule. The periodic table is for single elements. So we have to double it. 38 grams. F2 is 1 mole. What happens?
Make sure you're writing down
Moles of F2, grams of F2 cancel, and we end with atoms of F. Okay. To Greg's point, please make sure you write this down. I'm actually going to take that a step away, and I'm going to say no. Okay? And the reason I'm going to say no is that what you are going to write down when Greg says to write this down is write down what? What's on the board. What's on the board is utterly useless. What you should be writing down was every single question I asked along the way. Okay? Because that's the process that allows you to solve this. What's written on the board is not helpful. When you go to the tutoring center and it says, I can't solve this, and they show you all the work that they went through and did, you now have the answer, which is great as long as you can bring the tutor to sit down next to you during the exam and just say, here's the exam, do this for me. If you can't do that, what you need to be doing is asking why each of those steps were being made along the way. The answer itself is utterly useless. Okay? To reiterate this a step further, how many people need more chemistry?
You mean after this class?
Yeah, after this class. We got 6 or 7 people. The rest of you, why the hell do you care about moles and molecules? You don't. What you care about is the process that we use to solve it. That's what you need. Okay? That process is critical. That process transfers to all of your other classes. For those of you who need more chemistry, this process also transfers to all of your other classes. And you need the practice because you will have to work with moles and molecules. Exciting. Okay? So when we go through and do this, you should not be waiting for me to solve the whole thing because that's not helpful. What is helpful is, I said, why did we place this number here? Okay? So you could write down the question and you could write down the answer for why we placed it there. That's a lot to write down. So it would be helpful if, say, I don't know, the lectures were recorded where you could go back and watch them again and be like, what specific questions did Mike ask? Well, I don't know how convenient it is. You got to go watch the lecture again. Okay? But this is where you can go through and take notes to reference those pieces. Does that make sense? We starting to get this? Okay? For those of you who just want to try and cram and memorize as much as you can to get out, I understand what you're trying to go through and do. You can circumvent the system. That's ultimately going to require rote memorization of the process, and hope to God I ask the exact same question. Okay? Which is fine. Probably won't ask the same question, but you're welcome to try that. Okay? So, let's make it more difficult. Chapter 9. So chapter 9 takes everything that we did in chapter 8 and it adds a whole new layer on top of it. Okay? That layer really isn't that much extra. Because the layer that we're adding is saying instead of looking at the chemical formula to convert substances, I need to look at a chemical equation. A chemical equation is what actually allows us to convert substances. The formula is kind of this hand-wavy, we're just saying, it happens. I don't know how it happens, it just does. Okay? A chemical equation is the actual chemistry that allows us to do those conversions. So the equation becomes much more relevant and useful. Okay? But to do a conversion through an equation, what do you need to have? An equation. So you would need to be able to recognize what type it is so that you could determine what the products were. You would need to be able to balance said equation, okay, so that you could get proper coefficients and proper subscripts to ensure that the numbers from your conversion that you're pulling out to use are actually valid. Okay? So all of that stuff we did in Unit 2 is going to haunt you a lot through this next section. Okay? So let's take a step away from Unit 2 a little bit, and let's make it a little bit easier. How do we build a bicycle? Wheels and frame. That's all I need. I just need to take a wheel and a frame, and I put them together, and I got a bicycle. So pedals and handles. Read the statement, please. Assuming there are just wheels and a frame. 2 wheels, 1 frame. So if I was to write that out, I could write it out as 2 wheels, 1 frame. Ta-da, bicycle.
Square? Exactly.
Oh. We could use a subscript. We could also go through and say, well, they were sold individually. They weren't sold as a package, so I would need 2 wheels. Okay? I now have a chemical equation. Well, what could I do with a chemical equation? Someone built 4 bikes. How many wheels and frames were used? Damn, you did that calculation really fast. What's your work? Multiply everything in the equation by 4. 4 bikes. Why did I multiply by bikes? 4 bikes?
Did you build 4 bikes?
Yeah, what? Just multiplying by 4 doesn't work. What was the process? Because believe it or not, the process to solve this is the exact freaking same as every other thing we've done. And so the instant that you step and say, well, I don't have to do that process, is the instant you're taking the opportunity to prove to yourself the process is awesome and will work every single time. And you're saying, I don't need that evidence. And then when we move to actually use it, like, well, shit, I don't know how the process works. What's the process? No, we do not start with what we have. What do we want?
Wheels and frames.
We want wheels. And frames. Can I solve for 2 things at once? No. So what does that mean? I need to solve for wheels and I need to solve for frames. Now what? What do I have? I have 4 bikes. Are 4 bikes the same thing as wheels and frames? What do we need to do? We need to do a conversion. In that conversion, I need wikes to become beals. I need bikes to become wheels. Where do I find the conversion factor that relates bikes and wheels? It's in the chemical equation. 2 wheels made 1 bike. Bikes to become frames. What's the conversion? 1 frame is 1 bike.
Do you put an E in bikes because it looks like Bix?
Okay. And now we can multiply across to get the answers. Does that make sense? Okay. That was our process. 6 wheels and 3 frames. How many bikes can be made? How'd you do that so fast?
Divide 3 by 6.
Okay. Divide 3 by 6, and you get 2. How many bikes can be made?
Just kidding. 3.
This is the exact thing I'm pointing out. Okay? This reflex to jump to an answer, you have to rein back just a little bit. Give me that half second where you freaking write out the work. Okay? And it can solve that small, simple mistake. Because by reflexing and jumping on an answer, you are very likely jumping on the wrong answer. Okay? Well, most of the time I'm right. What's your most of the time? Is this 70% of the time? Is that all you want? Just barely passing C? Is it 80% of the time? The process that I'm giving you works arguably 100% of the time. Okay? It just comes down to, did you follow the process? Okay? If you don't follow the process, that's when it starts to fall apart. Okay? So arguably I would say the process works 95% of the time. Give it a little bit of error. I'm pretty sure everybody's going to be happy with that response. Okay? That's why I'm pushing the process. That's it. That's the only reason. Because I want you to be right 95% of the time. Okay? It's a hell of a lot better than me. I'm at like 80. Okay? Make sense? Given just 2 wheels, how many bikes can be made? God, ambiguous questions. Chemistry has a bad habit of asking this question, expecting the answer of 1. Okay? So we have to watch out for that. There's vague language in how chemists phrase that question because they're assuming there's enough of the other species. Okay? It's something that I watch out for, and I try to ensure that my questions make that assumption very clear. So what that question should say is, given 2 wheels and however many bikes I need, or frames I need, how many bikes can be made? 1. Does that make sense? Yeah. Okay. So be careful with the language that's presented. If you encounter something like that on the exam, what you could look for is immediately the none of the answers are provided answer. Okay? And that is a possibility. If you don't see that, you should raise your hand and be like, Mike, did you be an idiot? And it'll be like, yeah, you're probably right, I was. Okay, shut your mouth. Okay? That's my 80%. Okay, does that make sense?
Yeah.
3 wheels and 2 frames, how many bikes can be made? But 2 frames, but only 3 wheels. So again, if you only go through and calculate it with frames, you end up getting the wrong answer. You have to calculate this question twice, once for each of those spots. It's dealing with something that you guys already have a physical phenomenon to wrap around, and that's why you're able to do it quickly. If you don't have that physical phenomenon, you can't do it quickly. That's why you need the process. 40 grams of wheels, 15 pounds of frames, how many bikes can be made?
How much does the bike weigh?
Okay. The chemical equation tells us what? The number of pieces, the physical object. It does not tell us the mass of those objects. So if we see a question that's given to us in measurements, the very first thing that we're going to have to do is convert those measurements into whole pieces. Once I have pieces, now I can use the chemical equation. Does that make sense? So we have to be thinking about that as we move through. Pieces are fantastic. What is our piece in chemistry? I'll kind of accept elements. Push that a little bit further. Atoms or molecules. How many times are you going to work with atoms or molecules? Not. Why not? They're too small to measure out. Okay, so more than likely, what are you going to be asked as far as our atoms and molecules? Moles of atoms. Moles of molecules. Because when we scale up to that mole value, we're now in a system that we can actually use and manipulate and deal with. So most of our calculations are going to go through moles. To answer this question, I had to get to an individual piece. Right? What is our piece in chemistry? Moles. So one of the most common places that you can start a calculation would be to convert whatever you're given into moles. Because moles now as a centerpiece can be used to calculate or convert into different substances. Moles are a pretty awesome universal unit. Does that make sense? So when stuck, convert to moles and just hope for the best. It doesn't always work, but it's a pretty solid place to start. Okay? So, this gives a lot of information in it, so let's slow this down a little bit. If we look at that chemical equation, that tells us that 2 molecules of NO react with 1 molecule of O2 to produce 2 molecules of NO2. Everybody agree? No. Okay. Where did those numbers come from? Coefficients. Okay. No, there's just something sitting in my throat. Okay. So what if instead of being 1 molecule, I decided to go to 1,000 molecules? Okay. It's proportional. It's still the number of those. So I could convert that molecule of O2 or molecules of O2 into molecules of NO by doing what? Molecules of O2, molecules of NO. What's that relationship? 2 to 1. Found where? In the balanced chemical equation. Okay? Which would then mean I would have 2,000 molecules of NO. Okay? That's the power of that equation. I could do that also out with the NO2. Okay? Can I measure 2 molecules easily? No. Can I measure 2,000 molecules easily? Still no. Okay? So, and we'll actually change it. We'll go a little bit easier. 1 molecule, no. 1,000 molecules, still no, right? Well, how about 6.022 times 10 to the 23rd molecules? Okay? That is now a large enough number that I can actually get a reasonable mass for that. Okay? If I happen to pick that random number of molecules, how many molecules of NO would need to be reacted? Twice as many. Okay? That ratio still holds true. Okay? And that still holds true for the end. The power of choosing 6.02 times 10 to the 23rd molecules is that I can now go through and say 6.02 times 10 to the 23rd is mole. Okay? So 1 mole. 1 times 6.02 times 10 to the 23rd. Which means the other ones become 2 times moles, or 2 moles. Okay? And that's what this slide, or what this chart is attempting to show. Which means from our chemical equation, we can use it to convert molecules, but more importantly, those coefficients can be used as moles. Okay? That's kind of neat. Just like our periodic table could give us AMUs per atom or grams per mole, our chemical equation can give us the relationship between atoms or moles. Right? Which one's more useful for us? Moles. Right? So when I go through to solve, as long as I get into moles, I can use that expression from the chemical equation. I can still use molecules. You don't want to. Okay? But you are welcome to use molecules if you would like in that conversion. What that's going to end up meaning is that when you do most of our problems, you'll have to use Avogadro's number twice. Okay? And it will cancel itself out. Okay? And it'll suck. Okay? Okay? So from this single expression, okay, and so when we talk about how to solve things, okay, I want a formula. I just want to memorize a formula to go through and solve. This is one of the reasons why we don't push formulas and we want the process. That single chemical equation could get us 6 different formulas. 1 equation, 6 formulas. Do you really want to memorize all the possible formulas? No. That's just 1 equation. We change it to a new equation, we get more formulas. Okay, so what we want to be able to do is to interpret the equation to get a process or get a relationship that allows us to solve. Kind of, sort of? Kind of, sort of. So, do it. How many moles of oxygen react with 2.25 moles of nitrogen? For those of you like, I can do this in my head, knock it off, write it down. What are we asked to solve for? Moles of oxygen. Did I write down moles of oxygen? No, what did I write? Moles O2. Should you have been able to write that just as quickly? Yes. Why? Unit 2. Unit 1. You should be making those abbreviations that fast. Okay? What were you given to start with? Moles of nitrogen, 2.25 moles of nitrogen. Notice again, we're showing it as diatomic. Over what? 1. I placed it in the numerator. Why did I do that? It's what I was given. But that could be a questionable choice. As long as you know why you're doing it. If you're like, I'm just going to do it there and hope it works out. That's fine. Right? But understand why you're making the placements of where you're doing it. Okay? Is moles of nitrogen the same as moles of O2? So what do you need to do? You need to convert. We need moles of N2 to become moles of O2. What is that conversion? So we go up to our chemical equation. What's our answer? So remember the question I asked? 100 times 1 was 100. What's 2.25 times 1? 2.25. How many moles of nitrogen do you need? Oxygen. 2.25. Doesn't have to be hard. Okay? Again, what we're pushing in the lecture is a lot of the process stuff so you can establish and get it through. Okay? Don't make it trickier than you have to. They're supposed to be straightforward. Okay? If you wanted to see the textbook, type it out. There's the textbook typed out. Units cancel, we get our answer. Cool? Okay. Why did we not do the moles of oxygen atoms to moles of oxygen gas? Were we asked for oxygen atoms? No. Okay. So you have to follow what the question asks. Just because we've done it doesn't mean you should repeat the calculation. Does that make sense? Okay. So, we look at some of the strengths behind this. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Oh my God, that's so freaking hard. It's the exact same as the bike question. What are you being asked to solve for? Moles of CO2. Given what? 1 mole of sodium hydrogen carbonate. For those of you taking notes, that's what should be written as soon as you start this question, not the question. Okay? Are those two the same thing? So what do we need to do? We need to convert. Okay? In that conversion process, let's go through and take a look. We've got our measurement moles and moles. So did the measurement change? Nope. So ideally we could leave that alone. Substance, sodium hydrogen carbonate versus carbon dioxide. Did the substance change? Yeah, so we need a substance conversion. Right? In that substance conversion, I want sodium hydrogen carbonate to show up in the denominator so that it can cancel. And I want CO2 to show up in the numerator because in the answer, that's where it shows up. Where do I find the relationship between those substances? From the balanced chemical equation. Was that equation balanced? Yeah, actually it is. And if we go through and look at it, 1 and 2, 1 CO2, 2 sodium hydrogen carbonates. Okay. What are the units? What are the measurement units for those? Moles. Why did I pick moles and not molecules? What am I trying to do? I want moles to cancel. That's why I picked moles instead of molecules. Okay? So the question allows me to do that, which means how many moles of CO2 do I get? I get 1/2 of a mole of CO2. Oh. Okay, so I'm just going to write a 0.5. Could we get 0.5 molecules of CO2? Why not? Molecule is the smallest thing we can get. We can't get half of that molecule because then it would no longer be that molecule. Right? So half of a molecule makes no sense. Why the hell am I allowed to say half of a mole? Because a mole is a whole lot more than half. I can absolutely cut a very large number in half. Okay? Come on. How many moles of sodium hydrogen carbonate are produced when 1 mole of sodium carbonate, water, and carbon dioxide mix? We're saying 1 mole of each. So if I take a mole of sodium carbonate and mix it with a mole of water and a mole of carbon dioxide, I would have 3 moles, right? Well, I would have 3 moles of those substances. Yeah, one of each. Would that be 3 moles of sodium hydrogen carbonate? Why not? When I take 2 bicycle tires in a frame, I get 3 bikes, don't I? Oh, that's not how it works, is it? You have to use the chemical equation to show those relationships. The mistake that's being made by saying I get 3 moles of product is what? I'm adding them up. So what am I trying to say is true that is not true? Einstein. Conservation of mass. Is a mole mass? No, a mole is a number of particles. Mass doesn't come into it in this case. Okay? So what we would have to go through and do is take a mole of each of those substances, convert it across to see how many moles could possibly come out. What do we end up finding out? It's 2. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? Remember that question about the vagueness? This is technically not vague because we're saying 2 moles of CO2 are consumed. For them to be consumed, what had to have been there? Everything else. Okay? So, how do I solve? What do I want for an answer? Grams, sodium, hydrogen. Was it sodium, hydrogen, carbonate? Yeah. Okay. What did I start with? Why am I placing it in the numerator? Is moles the same thing as grams?
No.
Is CO2 the same thing as sodium, hydrogen, carbonate?
No.
Why am I placing it in the numerator? I'm trying it to see if it works. It does. Okay? So, both the measurement changed and the substance changed. Which do you want to look at? So I want CO2 to become sodium hydrogen carbonate. Where do I find that? The balanced chemical equation. And the balanced chemical equation tells me 1 mole of CO2 is 2 moles of sodium hydrogen carbonate. Why did I pick moles? I want that unit to cancel out. That's why I picked moles, not molecules. I now have 2 moles of sodium hydrogen carbonate. Is that the same thing as grams of sodium hydrogen carbonate? No. So I need moles of sodium hydrogen carbonate to disappear. What do I need 2 up here? Grams of sodium hydrogen carbonate. Where do I find that? That comes from the periodic table. Oh, look, we started class with that. That's chapter 8. So we'd go to the periodic table and we would add up all the masses there. Because I round 23 plus 1 plus 12 plus 48. I heard someone say 74. Were you right? No. It's 80 flat? 84 grams per mole. What happens? Moles cancel. What do I have? Grams of sodium hydrogen carbonate. What we just did was stacked chapter 8 and chapter 9 back to back. Was the process any different? No. It's just a question of where the information was found to do those conversions. Okay? That's what makes this unit challenging. You have to know where to find that information. Okay? We'll pick up there on Monday. I'm not going to lie, we are going to pick up the pace a little bit.